Hello there, and welcome to the Sleepy Science Channel. Tonight, we drift into one of the strangest ideas modern science has uncovered. It is something that fills the universe. It shapes the future of galaxies. Yet no telescope has ever seen it, and no laboratory has ever captured it. Astronomers call it dark energy. When scientists first realized that the universe is expanding faster with time, the discovery felt almost impossible. Gravity should slow the cosmos down. Galaxies should tug on one another across the vast darkness. Instead, the great distances between them continue to stretch more and more quickly. Something is pushing the universe outward. This hidden influence may make up most of the cosmos. It may live in empty space itself, and it may determine how the universe ends, billions upon billions of years from now. Tonight we will wander through the discoveries, the clues, and the mysteries that surround this invisible force. From exploding stars to giant galaxy maps, from Einstein's equations to bold new theories about space and time. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, there is nothing you need to do but get settled in. Let your shoulders soften, let your eyes grow heavy, and allow the day to gently fade away. As the universe stretches far beyond imagination, we will explore the mystery together. Let's begin. Dark energy is making the universe expand faster. For most of human history, that would have sounded backwards. When something moves apart, we expect gravity to pull it back and slow the motion down. That is what many astronomers expected for the universe as well. After the Big Bang, all the matter in space should have acted like an enormous cosmic break. Instead, the opposite seems to be happening. The farther we look, the more clearly we see that expansion is speeding up with time. It is as if the universe pressed the accelerator long after the journey began. That single idea changes the emotional scale of the cosmos. Space is not just stretching. It is becoming more restless, more dynamic, more surprising than anyone guessed. A universe that accelerates is not simply large. It is active in a way that feels almost startling, and it forces us to ask what invisible influence could be powerful enough to challenge gravity itself across the deepest reaches of existence. Most of the cosmos may be made of something unknown. That is one of the most humbling discoveries in all of science. Everything familiar, from mountains and oceans to stars and the atoms in your body, appears to be only a small fraction of reality. The rest seems to belong to dark matter and dark energy, two ingredients that do not fit neatly into ordinary experience. In other words, the bright universe we can see may be more like a thin surface layer than the main substance of the whole. This changes the feeling of the night sky. The glowing stars no longer look like the complete story. They look like islands in a vast hidden ocean. It also changes our place in the universe. Human beings did not just discover new planets or distant galaxies. We discovered that the familiar world is surrounded by a much larger mystery. The cosmos is not mainly made of things we understand well. It may be shaped most deeply by ingredients whose true nature is still unknown. The universe once slowed down, then mysteriously started speeding up. That twist gives cosmic history the feel of a plot change no one expected. In the early universe, matter was packed more densely, so gravity had a stronger grip on expansion. For billions of years, that pull appears to have been winning, and the growth of space should have been easing back. Then, as matter spread out and thinned, something else began to matter more. Around 5 billion years ago, the trend seems to have reversed. Expansion stopped losing speed and began gaining it. the universe changed character. It shifted from a story dominated by attraction to one shaped by a strange outward push. That means the cosmos has not always behaved the way it does now. It has gone through eras, almost like chapters. We live in the accelerating chapter, which makes this moment in cosmic time especially revealing. To understand why that change happened is to ask why the universe entered a new phase at all. Dark energy may shape the ultimate fate of everything. This is why the subject feels so much larger than one more scientific mystery. It is not only about what the universe is doing now. It is about where all of existence is heading. If the accelerating expansion continues forever, distant galaxies will drift farther away until the sky becomes emptier than any living being today could imagine. Over immense spans of time, the cosmos may grow colder, darker, and more isolated. Yet that is only one possibility. If the unknown driver behind expansion changes, then the future could look very different. Some theories allow a gentler ending. Others lead to outcomes far stranger. The important point is that the destiny of stars, galaxies, and the great visible architecture of the universe may depend on a force we still cannot explain. Few scientific ideas reach that far. This one reaches to the end of time itself and asks whether the final shape of reality is being decided by something hiding in the fabric of space. We discovered dark energy by watching distant exploding stars fade. That is part of what makes the story so beautiful. The clue did not come from some giant cosmic machine or from a dramatic object tearing through space. It came from careful attention to light. Certain stellar explosions, called Type 1a supernovas, brighten in a predictable way, which lets astronomers use them as distance markers across the universe. By comparing how bright they should appear with how redshifted their light had become, researchers could test how expansion changed over time. They expected those ancient explosions to suggest a universe slowing under gravity. Instead, the supernovas looked dimmer than expected, which meant they were farther away than that picture allowed. Space had stretched more than predicted, while their light traveled toward us. An entire new cosmic mystery emerged from tiny measurements of faint points of light. The discovery reminds us that some of the biggest revolutions in science begin in patience, in precision, and in the willingness to trust a strange result. Empty space itself may carry a hidden energy. That idea can feel almost impossible at first, because empty space sounds like the one place where nothing should happen. Yet modern physics does not treat the vacuum as a featureless blank. Even in regions with no stars, no dust, and no planets, space still has structure. Fields exist there. Quantum theory suggests restless activity there. And one possibility is that space itself has an intrinsic energy that does not disappear when matter is absent. If that is true, then the emptiest parts of the universe are not truly empty at all. They are filled with a property that keeps acting everywhere, all the time. This is one reason the mystery feels so profound. The answer may not lie in some rare object hidden in a remote galaxy. It may lie in the background nature of reality itself. The void between galaxies could be doing something extraordinary, quietly shaping the largest possible story with an influence built into space at its most fundamental level. Dark energy seems gentle, yet it outruns gravity across the cosmos. That contrast is one of its strangest features. On everyday scales, and even on the scale of galaxies, gravity still rules. It binds you to Earth. It keeps the moon in orbit. It holds stars inside galaxies, and galaxies inside clusters. Nothing around us looks like it is being torn apart by some wild, repulsive force. Yet across the greatest distances, the balance changes. Over immense expanses of nearly empty space, the slow, persistent effect linked to acceleration begins to win. That means the mystery is not dramatic in the ordinary sense. It does not roar or flash. It accumulates. It works through distance and patience. Its power shows up only when the arena becomes vast enough. That makes it feel almost more uncanny, not less. The force shaping the future of the universe does not announce itself in local chaos. It reveals itself only in the grandest measurements, where its steady influence can overcome the pull that built stars, galaxies, and much of the visible universe. Galaxies are not just fleeing, the space between them is swelling. That distinction matters because it changes the mental picture completely. It is easy to imagine galaxies as cosmic shrapnel thrown outward through a pre-existing emptiness. But the deeper idea is stranger. In the large-scale view of cosmology, the distances grow because space itself expands. A helpful image is raisin bread rising in an oven. The raisins are not racing through the dough under their own power. The dough between them is stretching, so every raisin sees the others move away. The universe behaves in a similar way on vast scales. This is why very distant galaxies can recede so quickly without breaking the rules of ordinary motion through space. The stage itself is changing size. Once that idea settles in, the universe feels less like an explosion into emptiness and more like a fabric whose very geometry evolves with time. The mystery behind acceleration then becomes even deeper, because it concerns the growth of the stage, not merely the motion of the actors upon it. The biggest thing in the universe may be the least understood. That sentence captures a deep scientific irony. Human beings have learned astonishing details about objects we can never touch. We know how stars shine. We know how planets form. We can trace the history of galaxies across billions of years. Yet the influence that may dominate the entire large-scale universe remains almost nameless beyond its effect. We call it dark energy, but that label is really a placeholder for ignorance. It tells us that something hidden is involved. It does not tell us what the thing actually is. This is what makes the subject so gripping. The mystery is not tucked away in a corner of science. It sits near the center of our best cosmic model. The largest pattern we know may depend on a component we cannot describe with confidence. In a way, the universe has revealed its outline before it has revealed its essence. We can map the consequences clearly, while the identity behind them remains one of the grand, unanswered questions. Dark energy could mean our best cosmic theory is incomplete. That possibility is one reason scientists treat the subject with such seriousness. Modern cosmology works remarkably well in many ways. General relativity describes gravity with extraordinary success. Observations of the cosmic microwave background, galaxy clustering, and supernovas fit together into a powerful overall picture. Yet the cause of accelerating expansion still resists explanation. The simplest option is that Einstein's equations already contain the answer in the form of a cosmological constant. Even that leads to a huge puzzle, because quantum theory seems to predict a vacuum energy wildly larger than what the universe allows. Other possibilities are even more radical. Perhaps the acceleration comes from a new field. Perhaps gravity behaves differently on the largest scales. Perhaps the framework itself needs revision. When a mystery survives inside a successful theory, it becomes especially exciting. It suggests that science is not finished with its deepest foundations. The next breakthrough may not just explain one strange effect. It may redraw our understanding of space, time, and reality. Dark energy does not clump into stars, planets, or galaxies. That makes it unlike almost everything people usually imagine when they think about cosmic ingredients. Ordinary matter gathers. Gas clouds collapse into stars. Stars collect into galaxies. Galaxies join vast clusters and superclusters. Gravity loves to make structure. It turns scattered material into islands, swirls, and great luminous cities of light. This mystery seems to behave very differently. It does not pile up in a glowing core or gather in invisible halos around worlds. As far as astronomers can tell, it stays spread out with remarkable smoothness. That matters because a smooth ingredient affects the universe in a very different way from a lumpy one. It does not build local objects. It shapes the broad background instead. It acts more like a property of the cosmic stage than a player moving across it. In a strange way, its refusal to gather is part of what makes it so powerful. By remaining everywhere, it can influence the overall expansion of the entire universe. It appears strongest only across the grandest cosmic distances. That is why no one notices it in daily life, and why its discovery took so long. On small scales, other forces overwhelm it completely. Earth holds you down. The sun keeps the planets in orbit. The Milky Way remains bound together. Even clusters of galaxies can resist the outward trend for immense spans of time. The strange influence only becomes obvious when astronomers compare regions separated by breathtaking distances, where the thinness of matter leaves little for gravity to grip. Then the balance changes. The larger the stage, the more the effect stands out. This gives the subject a remarkable emotional scale. The clue does not live in one object or one event. It emerges only when the universe is treated as a single whole. In that sense, the mystery is almost too large to notice directly. It hides beneath local order and reveals itself only when human beings learn to think in billions of light years and in the history of the cosmos itself. You cannot bottle dark energy, touch it, or shield against it. That makes it feel almost dreamlike, though the evidence for its effects is serious and precise. We are used to the idea that a real thing can be held, stored, blocked, or measured in a lab by direct contact. Light can be trapped in instruments. Particles can strike detectors. Magnetic fields can be bent and studied. This cosmic mystery refuses that kind of intimacy. No container could gather it from the room around you. No wall could keep it out. No spacecraft could fly through a dense pocket of it and return a sample. It does not behave like a substance drifting past us in streams. Instead, it seems woven into the large-scale fabric of the universe itself. That changes the style of the hunt. Scientists are not stalking a rare particle through a machine. They are reading the behavior of the cosmos and asking what invisible ingredient could make the whole vast system move this way. Astronomers infer dark energy from motion, not from direct detection. That means they solve the mystery the way a detective might solve a case without seeing the culprit. They study the traces left behind. They compare how far away distant objects are with how much the universe has stretched their light. They watch how galaxies gather across time. They examine how cosmic structure grows and how the geometry of the universe reveals itself through enormous surveys. From those patterns, a picture begins to emerge. Something unseen is affecting the expansion history of the cosmos. This indirect style of reasoning may sound weaker than direct detection, but in astronomy, it is often the only path available. No one has touched a black hole either, yet their influence is unmistakable. The same is true here. The unseen presence is known through its consequences. In a way, that makes the subject even more compelling. It asks the mind to work outward from evidence, and to accept that reality can announce itself clearly even while hiding its face. Dark energy was discovered surprisingly late in scientific history. That is striking because the universe has been expanding since long before telescopes existed. Yet the accelerating part of the story only came into focus near the end of the 20th century. By then, people had already split the atom, walked on the moon, and mapped the afterglow of the Big Bang. Science had transformed daily life and rewritten humanity's picture of the cosmos many times over. Even so, one of the largest features of reality remained hidden in plain sight. The reason is not that the clue was tiny, but that it required special tools, deep surveys, and a new level of precision. Earlier generations could discover that galaxies are moving apart. Discovering that the rate changes over time was a subtler challenge. This gives the subject a wonderfully humbling quality. The mystery was not buried in some inaccessible corner of nature. It was embedded in the overall behavior of the universe, waiting until human beings became careful enough to notice. For decades, many scientists expected cosmic expansion to slow forever. That expectation was not a careless guess. It came from a very natural reading of gravity. If the universe began in a hot, expanding state, then all the matter inside it should pull against that expansion. The question seemed to be how much slowing would occur. A dense cosmos might eventually halt and collapse. A thinner one might keep expanding, but with the pace always easing downward. Those were the kinds of futures many researchers debated. The crucial assumption was that gravity set the long-term trend. Then observations forced a much stranger answer. The slowdown picture was not merely incomplete. It pointed the wrong way for the later universe. This reversal is part of what gives the topic its dramatic power. Science was not just missing a detail. It was surprised at the level of direction itself. The cosmos was not coasting under a familiar script. It was following a deeper one, and the old expectations suddenly looked like only half the story. Instead, distant supernovas arrived dimmer than expected. That tiny difference in brightness carried enormous weight. These stellar explosions were chosen because they can serve as dependable beacons across huge distances. Astronomers could compare how bright they appeared with how much their light had been stretched on its journey. Under the old picture, the numbers should have lined up one way. They did not. The explosions looked fainter, which meant they were farther away than a steadily slowing universe would predict. Light that had traveled for billions of years had preserved a message, and that message said space had expanded more than expected while the light was in flight. There is something deeply thrilling about that. The clue was not a thunderclap. It was a subtle mismatch in ancient starlight. Yet from that mismatch came one of the boldest claims in modern science. A few careful observations of faraway cataclysms suggested that the universe was not obeying the future that gravity alone seemed to promise. That dimness helped reveal a universe-changing course. Brightness might sound like a simple detail, but in cosmology, it can become a record of history. When those faraway explosions appeared fainter than expected, the effect was not just a statement about distance. It was a statement about time. It implied that the universe we see today is not expanding in the same spirit as the universe of the distant past. The cosmic story had bent. To understand why, imagine reading an old travel log and realizing the road itself changed shape while the traveler was moving. That is close to what astronomers faced. The faintness pointed to a difference between earlier expansion and later expansion. It suggested a turning point in the long behavior of the cosmos. The importance of that clue lies in its logic. A small shift in observed light became evidence that the universe has a changing tempo. The largest known system was not repeating one pattern. It was evolving from one regime into another. Dark energy entered cosmology through one of astronomy's biggest shocks. The shock came not because the measurements were sloppy, but because they were good enough to challenge a deeply rooted expectation. Two major research teams, working independently, studied distant supernovas in the 1990s. Both were trying to learn how cosmic expansion behaved over time. Neither group set out hoping to discover an accelerating universe. In fact, the result was surprising enough that caution came first. Scientists checked calibrations, dust effects, and possible biases. They knew that extraordinary conclusions demand extraordinary care. Yet as the evidence strengthened, the astonishing interpretation survived. The universe seemed to be speeding up. That gave cosmology one of its rare moments when the floor shifts beneath an entire field. A result appears that is difficult to fit into the familiar framework, and suddenly the questions become larger than before. Such moments are precious in science. They reveal that reality is still capable of overturning confident expectations with something stranger and more beautiful. Its discovery won the Nobel Prize in Physics. That honor signaled more than admiration for clever observing. It marked the discovery as a turning point in humanity's understanding of the universe. In 2011, Saul Perlmutter, Brian Schmidt, and Adam Rees received the prize for showing that cosmic expansion is accelerating. Nobel Prizes are not given lightly, and this one reflected how profoundly the result changed modern cosmology. The award also tells a human story. It reminds us that the mystery was uncovered through years of collaboration, competition, patience, and repeated checks of difficult data. The prize did not mean the subject was solved. Quite the opposite. It celebrated the fact that a major new question had been opened with convincing evidence. That is a beautiful feature of science. Sometimes the greatest achievement is not closing a case, but proving that reality is stranger than expected. In this case, recognition came because astronomers showed that the universe contains a profound secret still waiting to be explained. Einstein once proposed a cosmic term that resembles dark energy. Long before astronomers found evidence for accelerating expansion, Einstein had already written down a mathematical ingredient that now feels eerily familiar. When he first applied general relativity to the universe as a whole, he expected the cosmos to be static and unchanging on the largest scales. His equations did not naturally allow that. Gravity made such a universe unstable. So he introduced an extra term that could counterbalance the pull of matter and hold the cosmos in place. At the time, this was a move to rescue a preferred picture of reality, not a prediction of acceleration. Yet the strange part is what happened later. The universe turned out not to be static at all, and the extra term seemed unnecessary. Then, decades after Einstein set it aside, observations of cosmic acceleration made that forgotten mathematical idea look newly important. Few moments in science feel more uncanny than watching an abandoned term return as a possible key to the universe. He later regretted it, then the universe revived it. There is a wonderful twist of drama in that story. After astronomers discovered that the universe is expanding, the extra cosmic term no longer seemed needed to keep everything still. Einstein reportedly came to view it as a mistake, a patch added for the wrong reason. Whether or not every famous quote about his regret is exact, the broad picture has become part of scientific folklore. He tried to force the universe into a static form, and nature refused. That might have been the end of it. Instead, late 20th century observations gave the old idea new life. Suddenly, the term that once looked like an embarrassment began to resemble a serious explanation for acceleration. It did not return because scientists were nostalgic. It returned because the cosmos itself demanded something like it. That reversal makes the whole episode feel almost theatrical. An idea introduced reluctantly, then cast aside, came back generations later as one of the most important possibilities in modern cosmology. The cosmological constant may be dark energy in simplest form. In this version of the story, The mystery is not caused by some changing field or exotic new substance drifting through space. It is built into space-time itself as a fixed property. The cosmological constant would mean the universe contains a steady background energy that remains the same as space expands. It does not dilute like matter. It does not thin out like radiation. As the universe grows larger and ordinary ingredients spread farther apart, that steady contribution becomes more important to the overall cosmic balance. One reason scientists take this idea seriously is that it fits a great deal of data remarkably well. A simple constant does a surprisingly good job describing the observed expansion history. That simplicity is both attractive and unsettling. It offers a clean explanation, yet it also leaves a haunting question. Why should empty space possess exactly that amount of energy and not some wildly different value? The neatness of the answer may hide an even deeper mystery beneath it. Vacuum energy is one leading idea for what dark energy is. The phrase sounds almost contradictory because a vacuum suggests absence, while energy suggests activity. Yet in modern physics, emptiness is not always truly empty. Fields can exist even where no particles are present, and the lowest possible state of those fields can still carry energy. If the vacuum of space has such an energy, then every region of the universe would contain it simply by existing. That makes the idea especially powerful. You would not need to sprinkle a new ingredient through the cosmos. The background of space itself would already provide it. This is part of why the concept feels so deep. It suggests the mystery is not hiding inside rare events or unusual places. It may be built into the baseline fabric of reality. The emptiest gulf between galaxies would still possess a hidden physical character. In that view, what we call nothing would turn out to be one of the most influential somethings in the entire universe. Quantum physics predicts empty space should not be truly empty. At the smallest scales, the universe behaves with a kind of restless refusal to sit perfectly still. Quantum theory describes fields that cannot simply switch off in a perfectly absolute way. Even their lowest energy state carries fluctuations and background activity. This does not mean particles are constantly popping in and out in the cartoonish way people sometimes imagine, but it does mean the vacuum has structure and physical consequences. Effects such as the Casimir effect hint that empty space can behave in measurable ways. That is why the mystery of cosmic acceleration reaches so far into fundamental physics. The idea that the vacuum has energy is not pure fantasy invented to explain one astronomical puzzle. It grows naturally from the logic of quantum theory. The real surprise is not that emptiness might have something going on. The surprise is that this tiny-scale quantum strangeness might connect to the fate of the entire universe, from microscopic fields all the way up to galaxies. The trouble is, theory predicts far too much vacuum energy. This is where the mystery stops being merely elegant and starts becoming almost absurd in scale. When physicists estimate the vacuum energy that quantum theory seems to allow, the result does not come out a little larger than what the universe appears to show. It comes out catastrophically larger. The difference is so extreme that it is often described as one of the worst theoretical predictions in all of science. If that enormous vacuum energy were really driving the cosmos, space would have behaved in a completely different way. Galaxies as we know them would never have formed. The universe would be unrecognizable. Yet reality looks calm enough for stars, planets, and people to exist. That means something in our understanding is badly incomplete. Either the naive calculation misses a profound cancellation, or the whole interpretation needs rethinking. What makes this so gripping is the scale of the mismatch. Nature is not nudging us toward a small correction. It seems to be pointing toward a major missing principle. That mismatch is one of physics' deepest unsolved problems. Scientists have given many hard puzzles this label over the years, but this one earns it. The conflict is not a minor tension between two measurements. It is a clash between the broad success of quantum field theory and the observed behavior of the universe on its largest scales. Both sides have tremendous credibility. Quantum theory powers vast areas of modern physics with astonishing accuracy. Cosmological observations also rest on multiple independent lines of evidence. Yet when vacuum energy is calculated in a straightforward way, the two worlds refuse to agree. That leaves physicists in a remarkable position. The mathematics that helps explain particles and fields seems unable to sit comfortably beside the cosmos we actually inhabit. The question is not just what number to plug into an equation. The question is why the vacuum does not overwhelm reality. Hidden in that gap may be a clue to deeper laws, a new symmetry, or a principle not yet imagined. Few problems feel more central than that. Dark energy may expose a crack between quantum theory and gravity. For more than a century, physics has had two towering successes that remain uneasy neighbors. Quantum theory governs the tiny world of particles and fields. General relativity describes gravity, space-time, and the large-scale structure of the universe. Each works magnificently in its own domain. Yet bringing them fully together has proved extraordinarily hard. The mystery of cosmic acceleration may be one place where that unfinished union becomes impossible to ignore. If vacuum energy from quantum theory plays a role in cosmic expansion, then gravity must respond to it. But the response we observe is nowhere near what simple theory suggests. That tension hints that our deepest descriptions are not yet speaking the same language. In that sense, the subject becomes larger than cosmology alone. It turns into a message from the universe about the unfinished foundations of physics. The accelerating cosmos may be telling us that our most successful theories are powerful, but not yet complete enough to describe reality as a seamless whole. It might not be energy at all, but altered gravity. That possibility changes the entire mood of the mystery. Instead of adding a new ingredient to the universe, some physicists ask whether the law of gravity itself behaves differently across truly immense distances. General relativity has passed many tests with stunning success, from planetary motion to black holes and gravitational waves. Yet most of those tests probe scales far smaller than the whole visible universe. So there is room, at least in principle, for gravity to act one way locally and another way across cosmic expanses. In that picture, acceleration would not come from a hidden energy filling space. It would come from the geometry of space-time responding in a more subtle way than Einstein's original theory predicts. That is a thrilling possibility because it would mean the universe is not being pushed by an unknown substance. It would mean the rules of attraction themselves need revision. Sometimes the biggest mystery is not a new thing in nature, but a familiar law revealing a deeper layer. Some theories replace dark energy with new cosmic laws. These ideas are bold because they do not simply tweak a constant or add a mild extra field. They rethink how the universe works at the most fundamental level. Some models modify the equations of gravity. Others imagine extra dimensions that alter cosmic expansion from behind the scenes. Still others explore new scalar fields, screening mechanisms, or changes in how space-time responds to matter over enormous distances. The common thread is a refusal to accept the mystery as merely a missing fluid in the universe. Instead, these approaches treat acceleration as a sign that the underlying rules may differ from the standard picture. That is one reason the subject remains so alive. It invites creativity at the edge of established science, while still demanding strict agreement with observation. Any new cosmic law must explain the expansion history without ruining the successes of existing physics. That is a hard balance to strike. Yet the reward would be immense, because a better law could transform our understanding of the universe from its smallest ingredients to its grandest fate. Dark energy only began dominating after matter spread itself thin. In the early universe, matter was crowded together far more densely than it is now. Galaxies had not yet fully assembled, and gravity had a stronger grip because there was simply more material packed into each region of space. As expansion continued, that matter became more dispersed. The cosmic pull did not vanish, but had lost strength as the universe grew roomier. If the hidden driver of acceleration stays roughly constant while matter thins out, then there comes a time when the balance changes. The old ruler weakens, and the quiet background starts to matter more. That turning of the scales is one of the most elegant ideas in cosmology. It means the mystery did not need to burst suddenly onto the scene. It could wait patiently while the universe aged. Only after matter diluted enough would the larger pattern shift and the long future of the cosmos begin to follow a different master than the one that shaped its youth. In the early universe, gravity mattered more than dark energy. That fact helps explain why the cosmos could build anything at all. If acceleration had dominated from the beginning, matter would have been driven apart too effectively for stars, galaxies, and the great web of structure to emerge in the way we see today. Instead, the young universe lived through an age when attraction had the upper hand. Tiny differences in density could grow. Clouds of matter could gather. The seeds left from the early cosmos had time to deepen into real structure. In a sense, there was a window of opportunity when gravity was strong enough to sculpt complexity before the later outward trend became dominant. That makes our existence feel tied to timing on a cosmic scale. The universe needed an era of construction before it entered an era of increasing separation. Without that earlier reign of attraction, the heavens might have remained much smoother and poorer, with far fewer places for stars to light and for life to eventually ask how everything began. Cosmic history may have a slow era and a speeding era. That gives the universe a rhythm rather than a single unchanging trend. It is tempting to imagine cosmic expansion as one simple motion that has just been continuing since the beginning. The real story appears more textured. There seems to have been a long chapter when the growth of space was being restrained, followed by a later chapter when the restraint weakened and the outward trend gained strength. That means the universe has a biography with changing conditions, almost like a landscape that looks different at dawn than it does at dusk. The expansion is not just happening. It has a history that can be reconstructed. When astronomers speak about cosmic acceleration, they are not describing a timeless property. They are describing a phase. That idea makes the cosmos feel more alive. It has passed through different regimes with different rules taking the lead. The challenge is to understand what set the boundary between those chapters and why the story turned when it did. Astronomers map that transition by looking deep into time. The beauty of cosmology is that distance doubles as memory. When light travels for billions of years before reaching Earth, it brings news from a much earlier universe. By collecting signals from objects at many different distances, astronomers can build a layered record of how expansion behaved across vast eras. Nearby objects reveal the more recent cosmos. Farther ones preserve older chapters. Piece by piece, that lets researchers trace when the slowdown of the past gave way to the speed-up of the later universe. It is not like reading one clear diary entry. It is more like assembling a long history from scattered messages arriving across time. That method turns telescopes into instruments of chronology as much as sight. They do not just show what is out there. They show when different patterns were in force. The hidden transition becomes visible through comparison, and the changing behavior of the universe emerges from a patient reconstruction of its own ancient light. Farther galaxies let us watch older chapters of expansion. This is one of the most astonishing gifts of light travel time. A distant galaxy is not only far away in space, it is also far away in the past, because its light began the journey long before human beings existed. When astronomers study such galaxies, they are not seeing the universe as it is at this moment. They are seeing how it looked when that light first set out. That means the sky is filled with different ages at once. Nearby galaxies show a more recent cosmos. Very distant ones show a younger one. By comparing them, scientists can ask how the expansion story has changed across time. This is why the universe feels less like a frozen picture and more like a layered archive. Every farther target opens an older page. Dark energy becomes a historical problem as much as a physical one, because understanding it requires seeing how the cosmos behaved in earlier ages and how that behavior differs from what the universe is doing now. Every telescope that sees deep space also sees ancient history. That idea never really loses its wonder. A telescope may seem like a machine for looking outward, but it is equally a machine for looking backward. Because light takes time to cross the universe, every deep observation reaches into the past. A galaxy 1 billion light-years away is seen roughly 1 billion years ago. An even more distant one appears in an even earlier state. So when astronomers point powerful instruments toward faint and remote objects, they are not simply surveying location. They are exploring time itself. This is what makes the study of cosmic expansion so rich. The evidence is not locked in fossils beneath the ground or in fragile written records. It is streaming toward us through space every night. The universe preserves its own past in light. To study dark energy, scientists use that natural archive, reading one era against another. The deepest images are not just beautiful. They are historical documents written across the sky. Dark energy is studied by comparing distance with redshift. That comparison sits at the heart of modern observational cosmology. Distance tells astronomers how far away an object is, which can be estimated using special kinds of supernovas, galaxy patterns, and other carefully calibrated methods. Redshift tells them how much the universe has stretched the light from that object while it traveled toward us. On their own, each measurement is interesting. Together, they become powerful. They allow scientists to test which expansion history best matches reality. If the universe had followed one pattern, a certain redshift would pair with one distance. If it followed another, the pairing changes. By collecting many such pairings across cosmic time, astronomers can check whether the cosmos slowed, coasted, or accelerated. The mystery reveals itself in the mismatch between expectation and observation. It is a subtle method, but a profound one. The hidden influence is not measured like a rock on a scale. It is inferred from the relationship between how far things are and how stretched their light has become. Redshift shows how much the universe stretched during light's journey. When light travels through an expanding universe, its wavelength is stretched along with space itself. That means the light arrives redder than when it began, with the shift toward longer wavelengths serving as a record of how much expansion occurred during the trip. The larger the redshift, the more the universe has grown while that light was crossing the cosmos. This makes redshift one of astronomy's most remarkable clues. It is not just a color change. It is a message encoded in the light itself about the history of space between source and observer. Distant galaxies arrive with their own expansion receipts attached. By reading those spectral changes, astronomers can learn how much the universe enlarged over the time the light was in transit. That is why redshift became essential to the dark energy story. It provides a direct window into cosmic stretching, and it turns starlight into evidence about the behavior of the universe on the grandest possible scale. Distance tells us how expansion behaved when that light began. That may sound strange at first, because distance feels like a simple measure of separation. In cosmology, it becomes something more subtle. To know how far away an object truly is, astronomers must account for how the universe expanded while its light was traveling. Different expansion histories produce different relationships between brightness, size, and travel time. So, a distance estimate is never just about where something sits. It also contains information about the behavior of the cosmos over the era when that light started its journey. In that sense, measuring distance is a way of probing the rules that were in force long ago. It lets scientists ask what kind of universe could have produced the signal we now receive. That is one reason dark energy research feels almost archaeological. Researchers are not simply cataloging remote objects. They are using those objects to reconstruct ancient cosmic conditions and to learn how the large-scale behavior of reality has changed over time. Together, they reveal a cosmic timeline of acceleration. Neither distance nor redshift is enough on its own to tell the full story. Redshift records how much stretching happened during the journey. Distance encodes how the universe's expansion history shaped the path the light followed. When scientists combine the two across many objects and many eras, a timeline begins to emerge. It becomes possible to test when gravity had the stronger role, when the balance started to shift, and how the later speeding phase developed. This is one of the triumphs of modern cosmology. Human beings cannot watch billions of years pass in real time, yet by comparing ancient light from many distances, they can piece together the changing behavior of the universe. The result is not a vague impression. It is a structured history with evidence from multiple epochs. The cosmos reveals that its expansion has not been simple or uniform. It has changed character, and that change points toward one of the deepest mysteries in all of science. Type 1a supernovas became the great clue to dark energy. These explosions earn their importance because they are both dramatic and dependable. A Type 1a supernova happens when a white dwarf in a binary system is pushed toward a critical limit, and the result is a brilliant thermonuclear blast. Because these events reach closely related peak brightnesses, astronomers can compare one with another across immense distances. That turns a violent stellar ending into a precision tool. What makes this so captivating is the contrast. A dying star in a faraway galaxy becomes a marker for the behavior of the whole universe. These explosions are bright enough to be seen across billions of light years, which means they let scientists compare nearby cosmic history with much older eras. Few objects could do that job. A single flash can bridge vast spans of time, and from those flashes came the evidence that expansion was not simply continuing. It was changing, and it was changing in a profoundly unexpected direction. They act like standard candles across enormous distances. Astronomers need more than bright objects. They need reliable ones. A standard candle is an object whose true brightness can be known, which means its apparent brightness can reveal its distance. If you know how luminous something really is, then its faintness becomes a clue rather than a mystery. Type 1a supernovas are precious for this reason. After careful corrections, they become some of the best distance markers in the universe. That is a wonderful idea in itself. A star can explode with such regularity that its death becomes a measuring stick. It is a kind of cosmic craftsmanship hidden inside catastrophe. Across enormous gulfs of space, these explosions allow astronomers to estimate how far light has traveled and how the universe behaved along the way. Without dependable candles of this sort, the expansion story would be much harder to read. The darkness between galaxies would stay more uncertain, and the evidence for acceleration would have arrived much more slowly. Their explosions help astronomers measure the universe itself. That sounds almost too grand to be true, yet it is exactly what happens. When one of these stellar blasts erupts in a distant galaxy, the light curve and spectrum reveal key information about its nature. From there, astronomers can estimate its intrinsic brightness and compare that with what reaches Earth. The result is not just a distance to one object. It becomes one point on a much larger map of cosmic expansion. Gather enough of those points, spread across many eras, and the universe begins to disclose its behavior. This is one of the great triumphs of observational astronomy. Human beings cannot stretch a tape measure across billions of light years, yet they can use physics to turn faraway explosions into tools of measurement. A star dies, and the cosmos becomes a little more legible. That transformation from local event to universal insight is part of what makes the subject so gripping. The scale of the question is enormous, yet the clues arrive through light. One stellar death helped uncover a cosmic mystery. There is something almost poetic in that. A single star ends its life in a blaze so bright that it briefly rivals the light of an entire galaxy. Then, far away, astronomers detect that glow and use it to ask what the universe is doing on the largest scale imaginable. The death of one object becomes part of a much greater revelation. This reminds us that cosmology is often built from particular events, not only broad abstractions. A supernova is personal in a cosmic sense. It belongs to one star, one system, one moment of destruction. Yet because light travels, and because physics leaves patterns in that light, the event can speak far beyond its birthplace. The great mystery of acceleration did not arrive as a voice from nowhere. It emerged from countless specific signals, each one tied to a real object in a real galaxy. The universe revealed its hidden trend by letting singular endings illuminate the story of everything. Baryon acoustic oscillations leave a fossil ruler in space. Long before galaxies formed, the young universe was filled with hot plasma, light and matter interacting in a dense cosmic fluid. Pressure waves moved through that early substance, rather like sound traveling through air, though on a scale almost beyond imagination. When the universe cooled enough for light to break free, those ripples froze their preferred scale into the distribution of matter. That scale remains imprinted in how galaxies are arranged today. Astronomers call this pattern baryon, acoustic oscillations, and it functions like a fossil ruler carried forward from the early universe into the present. The beauty of the idea is hard to overstate. A vibration from the infant cosmos still echoes in the large-scale arrangement of galaxies billions of years later. By measuring that preferred separation, scientists can test how the universe expanded across time. The ruler is ancient, but it still works, and it offers a completely different path toward the same deep mystery. That ruler helps scientists track expansion across billions of years. A measuring stick is only useful if its true size is known, and the fossil scale left by early cosmic ripples gives astronomers exactly that advantage. Because the preferred separation in galaxy clustering can be predicted from early universe physics, researchers can compare its known size with how large it appears at different distances. That comparison reveals how space has stretched across cosmic history. It is a brilliant method because the ruler was not built by humans. The universe made it for us in its youth, then preserved it in the arrangement of galaxies. When enormous surveys map where galaxies sit, they are also reading this ancient yardstick. By seeing how the pattern changes with redshift, scientists can trace how expansion unfolded over billions of years. This gives dark energy research a wonderfully layered quality. A feature born in the first chapters of cosmic history becomes a tool for understanding the later chapters, when acceleration seems to have taken hold. Galaxy surveys can test dark energy without using supernovas. That independence matters because science becomes stronger when different methods converge. Supernovas are powerful, but astronomers do not want a grand conclusion resting on only one kind of object. Large galaxy surveys offer another route. By mapping millions of galaxies across huge volumes of space, researchers can study large-scale structure, clustering patterns, and the fossil ruler left by early cosmic ripples. These maps reveal how the universe expanded and how matter gathered over time. That means the mystery can be tested through statistics and pattern, rather than through stellar explosions alone. There is something thrilling about that shift in perspective. Instead of waiting for rare flashes, scientists can read the broad architecture of the cosmos itself. The arrangement of galaxies becomes evidence. The sky turns into a giant data set with history written into its shape. When those independent maps point toward the same strange conclusion, the case for acceleration becomes far more convincing and far more profound. Multiple methods now cross-check the same strange conclusion. This is one reason the subject commands so much respect. In science, a surprising result becomes far more persuasive when it survives attacks from different directions. Supernovas gave the first major clue, but they are no longer alone. Baryon acoustic oscillations, measurements of the cosmic microwave background, weak lensing and galaxy clustering all contribute pieces of the larger picture. Each method relies on different observations, different assumptions, and different kinds of physical reasoning. That variety is exactly what gives the conclusion its strength. If only one technique suggested acceleration, doubt would remain much heavier. But when many approaches, each with its own vulnerabilities, begin to agree, the mystery hardens into a serious feature of reality. The agreement does not mean every detail is settled. Far from it. Yet it does mean the broad phenomenon is not likely to be a mirage. The universe seems to be telling the same strange story in several different dialects, and astronomers have learned to hear the common message. Weak gravitational lensing can reveal dark energy through warped light. Gravity does more than pull objects together. It also bends the path of light, which means the mass spread across the universe can subtly distort the appearance of distant galaxies. This effect is called weak gravitational lensing, and it is extraordinarily delicate. Astronomers look for tiny statistical stretches and alignments in the shapes of huge numbers of galaxies. From that, they can infer how matter is distributed and how cosmic structure has grown over time. This becomes a dark energy test because the growth of structure depends on the competition between attraction and expansion. If the universe is accelerating, that changing backdrop influences how matter clumps and how lensing patterns develop. What makes this method so mesmerizing is its subtlety. The cosmos leaves clues not through one dramatic event, but through faint warps spread across the sky. Light from distant galaxies arrives gently bent, and in those bends lies information about the invisible forces shaping the history of the universe. Even galaxy shapes carry clues about cosmic expansion. At first glance, a galaxy's shape might seem like a local detail, something determined only by its own stars, gas, and collisions. Yet when astronomers examine immense populations of galaxies, their apparent shapes become part of a larger statistical signal. Weak lensing slightly shears those shapes as light passes through uneven matter on its way to us. No single galaxy tells the story clearly, because its original form is unknown. But across millions of galaxies, patterns emerge. Those patterns reveal how matter is arranged and how strongly structure has grown through time. That growth is sensitive to the universe's expansion history, which means the outlines of distant galaxies can become indirect witnesses to dark energy. This is one of the most astonishing features of modern cosmology. Even the subtle appearance of remote galaxies carries information about the fate of the cosmos. Shapes that seem incidental at first can, in aggregate, help expose the hidden influence guiding expansion on the largest possible scale. Dark energy changes how quickly cosmic structure grows. The universe is not only expanding, it is also assembling patterns. Matter gathers into filaments, clusters, and vast walls that stretch across space like architecture on a cosmic scale. The pace of that growth depends on a contest. Gravity tries to pull matter inward and deepen structure. Accelerated expansion makes that gathering harder by increasing the distances matter must overcome. Because of that, the mystery does more than influence the size of the universe. It also changes how richly textured the universe becomes. A cosmos with stronger acceleration grows structure less eagerly. A cosmos with weaker acceleration gives gravity more time to work. This is why astronomers care so much about the distribution of galaxies and clusters. Those patterns are not just scenery. They are records of a long struggle between attraction and expansion. By measuring how much structure formed, scientists can learn how powerfully the hidden driver has been shaping the universe over billions of years. It helps determine whether galaxy clusters form faster or slower. Galaxy clusters are among the largest bound structures in the universe, with hundreds or even thousands of galaxies held together by gravity. They do not appear instantly. They grow gradually as matter falls inward over immense spans of time. That makes them excellent witnesses to cosmic conditions. If expansion is being pushed harder outward, then matter has a tougher job assembling into these giant systems. Growth slows. If the outward influence is weaker, gravity can build clusters more efficiently. In that sense, every great cluster in the sky is part of a long census of cosmic possibility. Astronomers can count how many clusters exist at different distances and compare those numbers with theoretical predictions. That comparison helps reveal how quickly structure formed in different eras. The result is wonderfully indirect. Scientists do not ask dark energy what it is. They ask the biggest bound cities in the cosmos how hard they were to build, and the answer helps expose the larger background force. A stronger dark energy influence can suppress large-scale growth. This is one of the clearest ways the mystery leaves fingerprints on the universe. Imagine matter trying to gather into ever larger structures under gravity. That process works best when distances stay manageable and attraction has time to strengthen tiny imbalances. But if expansion becomes more dominant, the growing separation between regions makes further assembly harder. The result is not that existing galaxies suddenly fly apart. Instead, the formation of new large-scale structure is slowed. The universe becomes less willing to knit itself into larger patterns. That idea gives dark energy a strangely selective power. It does not erase what has already formed on smaller bound scales, yet it can limit what the future cosmos will manage to build. Astronomers test this by studying how structure growth changes across time. If the hidden influence has been stronger, the large-scale universe should look more restrained. In that restraint, scientists can read the history of a force no one has ever directly seen. The cosmic web remembers the balance between gravity and expansion. Across the largest scales, galaxies are not scattered randomly. They trace a vast network of filaments, knots, and voids, known as the cosmic web. It is one of the grandest patterns in nature, and it formed through the long interplay of matter, motion, and gravity. Yet the web is not only a map of attraction. It also preserves the history of expansion. The thickness of filaments, the growth of clusters, and the emptiness of great voids all depend on how strongly gravity could gather matter while the universe itself was stretching. That is why the web can be read almost like memory made visible. It carries the imprint of competing influences acting across cosmic time. The structure we observe today is the result of what the universe allowed matter to become. In that sense, the web is not just beautiful. It is historical evidence. Its form tells us how the cosmos balanced inward, pull against outward growth, while shaping the largest patterns we know. Dark energy affects the universe's geometry as well as its future. When people first hear about this subject, they often think only about destiny, about whether the cosmos will expand forever or drift toward some distant ending. But the mystery also connects to geometry, which means the very shape and distance relations of the universe on large scales. In cosmology, geometry is not an abstract side topic. It affects how light travels, how far objects appear, and how different parts of the cosmos line up in observation. If the hidden driver changes the expansion history, then it also changes the geometric framework through which astronomers interpret the sky. This is why measurements of angles, distances, and large-scale patterns all matter so much. The question is not only where the universe is going, it is also what kind of stage it has been all along. A force that influences geometry is not merely steering events. It is participating in the form of the cosmos itself, in the structure of space across the widest imaginable scale. It influences distance, time, structure, and cosmic scale. Few ideas in astronomy reach across so many layers of reality at once. The mystery affects how far away distant objects appear when their light reaches us. It affects time by changing how expansion unfolds through different eras of cosmic history. It affects structure by altering how easily matter can gather into clusters, filaments, and the broad web of galaxies. It affects scale because the biggest measurements in the universe depend on the background expansion that shapes everything else. This wide reach is part of what makes the subject so compelling. It is not one narrow puzzle tucked into a specialized corner of physics. It touches nearly every major way astronomers describe the cosmos. That is why so many different observations become relevant to the hunt. The same hidden influence can leave traces in brightness, clustering, lensing, and geometry. A mystery with that many consequences cannot be dismissed as a minor curiosity. It belongs near the heart of our picture of the universe. Even the largest maps of galaxies are really dark energy tests. At first glance, a galaxy map looks like a census of islands of light. You see positions, densities, clusters, and sweeping filaments spread across colossal volumes of space. Yet beneath that visual richness lies a deeper purpose. These maps are not just atlases. They are experiments. The arrangement of galaxies carries information about how the universe expanded and how matter grew into structure over time. By comparing real maps with theoretical models, astronomers can ask which version of cosmic history best fits the observed sky. That turns every large survey into a test of the hidden driver behind acceleration. The more galaxies included, and the farther the map reaches, the more demanding the test becomes. This is one of the marvels of modern science. A project that seems like mere cartography becomes a way to probe fundamental physics. The universe is mapped not only so we know where galaxies are, but so we can learn why the cosmos took this shape at all. Cosmology studies dark energy by mapping patterns, not objects alone. That difference is important. A single galaxy can be beautiful and informative, but the deepest clues often emerge only when many galaxies are seen together. Cosmology looks for statistical structure, for recurring separations, for distortions, for clustering strength, and for the evolving relationships between vast populations of objects. In other words, the science is often less about individual celestial bodies than about the patterns they collectively form. This gives the field a special kind of power. It can extract meaning from arrangements too large for any one object to explain by itself. A lone galaxy may tell a local story of stars and gas. A million galaxies can tell a cosmic story about expansion and gravity. That shift from object to pattern is one reason dark energy research feels so modern. It depends on seeing the sky as data woven into structure. The hidden influence may never appear as a single thing to point at, but it may still reveal itself through the grand statistical design of the universe. The universe itself becomes the laboratory for this mystery. That is both inspiring and humbling. In most sciences, experiments happen in controlled rooms, with instruments built to isolate specific effects. Here, the experiment is far larger than any human could construct. The testbed is the cosmos itself, with galaxies as tracers, light as messenger, and billions of years as part of the setup. Astronomers cannot turn the force on and off. They cannot adjust one parameter and rerun the universe from the beginning. Instead, they must observe carefully, compare models, and treat the sky as evidence left behind by natural processes operating on the grandest scale. This makes cosmology feel almost like forensic science for reality itself. The lab is already running and has been running since the earliest moments of cosmic history. Human beings arrive late and try to reconstruct what happened. That challenge gives the subject its distinctive drama. The universe is not merely what scientists study. It is also the apparatus through which the hidden answer must be found. Every billion light-years adds new leverage to the puzzle. Distance matters here in a very special way. A nearby observation can tell astronomers about the recent universe, but it cannot reveal much about how cosmic behavior changed across deep time. To test dark energy properly, scientists need reach. They need objects and patterns spread across enormous ranges of distance, so they can compare different ages of expansion against one another. Each additional billion light-years opens access to another stretch of history, another chance to see whether the hidden influence behaved consistently or evolved with time. That is why modern surveys push so hard toward great depth as well as wide coverage. More reach means more leverage over the mystery. It allows theories that once looked similar to be pulled apart by evidence. The farther the map extends, the longer the baseline for measuring the universe's behavior. In a subject like this, depth is not just grandeur for its own sake. It is what turns vague suspicion into a sharper and more testable cosmic question. Dark energy is not the same thing as dark matter. The names sound similar enough to confuse almost anyone at first, yet they describe two very different cosmic mysteries. Dark matter reveals itself through extra gravity. It helps hold galaxies together, bends light around clusters, and acts as an invisible mass that ordinary matter seems to feel. Dark energy shows up in almost the opposite way. It is linked to the large-scale speeding up of cosmic expansion. One mystery helps explain why structures stay bound. The other helps explain why the broad universe grows apart more rapidly with time. That contrast is essential because the modern cosmos contains both hidden ingredients at once. Astronomers did not discover one strange, invisible thing and give it two names. They found two different gaps in understanding, each with its own evidence and behavior. Learning that distinction is like realizing the dark side of the universe has more than one secret. The invisible cosmos is not a single mystery. It is a whole landscape of them. Dark matter pulls matter together. Dark energy drives space apart. That single contrast captures one of the strangest balances in all of cosmology. Dark matter acts like extra gravitational glue. It deepens the pull that gathers gas into galaxies and galaxies into larger systems. Without it, much of the structure we see in the universe would be far harder to explain. dark energy points in a different direction. It is associated with the large-scale stretching of the universe becoming more dominant over time. So the hidden cosmos contains both a builder and a separator. One helps matter gather into great structures. The other changes the broad stage on which those structures live. This is part of what makes the universe feel so alive with tension. Its history is not driven by one simple trend. Competing influences shape it at different scales and in different eras. The heavens are neither only pulling together, nor only drifting apart. They are doing both, and the outcome depends on which hidden influence has the upper hand. One helps build galaxies, the other separates them faster. That contrast gives the universe a strange kind of double architecture. Dark matter helps provide the gravitational wells into which ordinary gas can fall. In those deep, invisible valleys, matter cools, gathers, and eventually forms galaxies full of stars. In that sense, one hidden ingredient helps construction begin. Dark energy works more through the widening of cosmic distance on the largest scales, which means far separated galaxies are carried away from one another ever more effectively over time. So the same universe that learned to assemble luminous islands also seems destined to increase the distance between those islands. That makes the cosmos feel both creative and dispersive at once. It can build magnificence locally while becoming more isolated globally. The stars you see belong to a universe that first learned how to make structure and then entered an era that increasingly thins out the connections between distant realms. Creation and separation are both written into the modern cosmic story. Dark matter shaped cosmic scaffolding before dark energy took over. A useful way to picture the early universe is as a place where invisible structure formed before much of the visible beauty arrived. Dark matter, because it does not interact with light the way ordinary matter does, could begin collapsing into broad frameworks early on. Those frameworks became the scaffolding for later galaxy formation. Ordinary gas then fell into those gravitational patterns, where stars and galaxies could grow. In that earlier era, the hidden mass component was crucial to the universe becoming richly structured, rather than smooth and empty. Much later, the influence linked to acceleration became increasingly important on the largest scales. So the two mysteries did not merely coexist. They helped govern different chapters of cosmic history in different ways. One was central to building the framework. The other came to dominate the long-range expansion of the stage itself. This sequence gives the hidden universe a narrative shape. First, the scaffold rose, then the spacing between its grandest structures began to grow ever faster. Together, they dominate the cosmic energy budget. That phrase sounds technical, but the underlying idea is wonderfully humbling. When cosmologists total up the contents of the universe, they do not find that stars, planets, gas, and dust make up most of what exists. Instead, the much larger share appears to belong to dark matter and dark energy. Ordinary matter, the substance that forms everything familiar to our senses, is only a smaller part of the total cosmic account. This changes the emotional tone of astronomy. The bright objects that fill photographs and the atoms that make daily life possible are not the main holders of cosmic influence. The universe is governed in large measure by ingredients we infer rather than directly experience. One unseen component shapes structure through gravity. Another shapes expansion through acceleration. Together, they outweigh the visible story by far. That realization can feel almost dizzying. The cosmos we know through sight and touch may be more like the illuminated fringe of a much larger reality ruled by hidden terms. Ordinary atoms may be only a small cosmic minority. Everything you have ever touched is made of ordinary matter. Skin, stone, water, flame, cloud, bone, wood, iron, and air all belong to the familiar atomic world. It is the world of chemistry, biology, and everyday human experience. Yet when astronomers study the universe as a whole, that familiar material seems to account for only a modest fraction of the total content. This means the matter of life and language may be cosmically outnumbered by invisible ingredients. That is one of the great perspective shifts modern science offers. We tend to assume the world we know best is the main substance of reality. Cosmology suggests otherwise. The visible and tangible may be a minority presence inside a much larger and stranger whole. There is something both unsettling and beautiful in that. The atoms that compose your body are not trivial. They are precious and intricate. But on the scale of the cosmos, they may belong to a smaller tribe than human intuition ever would have guessed. Everything familiar may be the universe's smaller ingredient list. Think of all the things human beings once believed were the main contents of the heavens. Fire in the stars, crystal spheres, ether. Then later, atoms, gas, dust, and radiant light. Each step brought deeper understanding, yet the latest picture is in some ways the most disorienting of all. It suggests that everything familiar to human senses and laboratories belongs to the lesser share of the cosmic recipe. The dominant ingredients may be things we have never directly held, seen, or fully explained. That does not make the familiar world less real. It makes it more remarkable. The universe produced a visible layer rich enough for stars to shine and for minds to arise, even though that visible layer may not be the main bulk of existence. In a way, cosmology has taken the ordinary world and turned it into a special case. What we call normal matter may not be the standard form of the universe, but a luminous minority within it. Stars, people, planets, and dust are not the main story. That is a startling sentence, because those are the very things that usually define the universe in our imagination. We think of astronomy as the study of glowing stars, strange worlds, comets, nebulae, and galaxies. We think of ourselves as living in a material cosmos, made mostly of the same atoms that fill the sun and the earth. Yet the deeper inventory suggests that the visible cast may not be the leading force in the cosmic drama. The actors we notice most easily could be only the bright surface of a story driven largely by unseen ingredients. This does not diminish the familiar universe. It reframes it. The stars become the illuminated windows, not the whole house. People become rare arrangements of ordinary atoms inside a reality whose dominant terms remain hidden. That perspective gives the sky a fresh kind of mystery. Even when we see it clearly, we may still be looking at only the smaller share of what is truly there. Most of reality may lie beyond everyday matter. That idea reaches beyond astronomy into philosophy, emotion, and the human sense of place. Everyday matter feels complete because it fills our direct experience. We build houses from it. We eat it, breathe it, study it, and become it. For thousands of years, it was natural to think that understanding matter meant understanding the world. Modern cosmology opens a larger possibility. The matter of daily life may be only the familiar corner of a much wider reality. Most of what governs the universe could belong to components that do not participate in ordinary experience the same way. That possibility does not make the world around us unreal. It makes it partial. We may live inside a cosmos whose dominant character is hidden behind appearances. There is something deeply moving in that thought. Reality might be far richer than intuition allows, and human beings may have reached a moment in history when they can finally sense just how incomplete their everyday picture has always been. Dark energy makes the familiar universe feel strangely incomplete. Before this mystery entered cosmology, it was easier to imagine that the major features of the cosmos were at least broadly understood. Expansion had been discovered. Gravity had a powerful theory. Galaxies and cosmic history were being mapped with growing confidence. Then, acceleration forced a new admission. The known ingredients were not enough. Something crucial was missing from the picture. That missing piece has a special effect on the imagination. It does not merely add one more object to the universe. It changes the completeness of the entire framework. The stars still shine, galaxies still turn, and gravity still shapes much of what we see. Yet the larger story now contains a gap at its center. The familiar cosmos remains beautiful, but it no longer feels finished. It feels provisional, like a draft that clearly works in many places while still lacking one of its most important explanations. That unfinished quality is part of the wonder. The universe is legible, but not yet fully understood. If dark energy stays constant, galaxies will drift into loneliness. That future begins on scales so large that no human lifetime could ever notice it. Yet it changes the long destiny of the cosmos. A constant background push would keep widening the gulf between groups of galaxies that are not already bound together. Great clusters and distant superclusters would recede farther and farther away, while local gravitational neighborhoods would become isolated islands in an ever larger sea of emptiness. This is not a violent ending. It is a slow separation, patient and relentless. The universe would keep expanding, but its visible richness would thin across the widest scales. A galaxy might still hold its stars for an immense time, and vocal groups might remain together, yet the broader cosmos would become less connected with every passing age. That is what makes the idea so haunting. The universe would not need to collapse or explode to become lonely. It would only need to keep growing, until distance itself turned companionship into memory. Distant galaxies may someday vanish beyond our cosmic horizon. This does not mean they would cease to exist. It means they would be carried so far away by expansion that their light could no longer reach future observers. There is a limit to what can remain visible in an accelerating universe. Beyond that limit, recession becomes so overwhelming that new light emitted toward us never overcomes the growing stretch of space. The galaxy is still there, continuing its own history, but it disappears from contact. That idea gives the cosmic horizon a strange emotional force. It is not just an edge of sight. It is an edge of future relationship. Objects can pass beyond it, not by moving through space like ships sailing over a sea, but because the sea itself changes too quickly for their signals to cross back. In such a universe, invisibility is not always about darkness or distance alone. Sometimes it is about the future shutting a window that the past once kept open. Future astronomers might see a far emptier sky. Imagine a civilization born trillions of years from now, inside one bound island of galaxies. If acceleration continues, much of the wider universe could already have slipped beyond view. Those future observers might look into the darkness and find only their local merged galaxy system, with little evidence that countless other galaxies once filled the cosmos. The sky would still contain stars and perhaps relic objects and ancient light if any remained detectable, but the grand extragalactic panorama we enjoy today could be gone. This possibility makes astronomy feel historically fragile. The truths we can discover depend partly on when we exist. Our era offers a sky rich enough to reveal expansion, cosmic structure, and the broader universe beyond our local home. A later era may hide much of that story. Knowledge is not only about intelligence and tools. It is also about timing. The cosmos may be giving us a view that future minds, however brilliant, would find much harder to reconstruct. Cosmic expansion can hide the universe from itself. That sentence sounds almost like a riddle, yet it captures a real possibility. If distant regions are carried apart fast enough, then observers in one region lose access to evidence from others. The universe does not merely spread out. It becomes less mutually knowable. Light is the great bridge between far places, but acceleration can weaken that bridge until whole realms slip out of reach. In that sense, the cosmos creates a kind of forgetting. Not because events are erased, but because the signals that would reveal them stop arriving. This is one of the most beautiful and unsettling consequences of dark energy. The universe is vast enough to generate its own hidden zones through time. A future observer may inhabit a cosmos that seems smaller than the one that actually exists, simply because expansion has cut off the view. Reality remains immense, but access to that immensity narrows. The universe can become less visible without becoming less real, which is a deeply haunting idea. Dark energy may slowly erase evidence of the Big Bang. Not the event itself, of course, but the clues that allow later observers to infer it. Today, one of the strongest pieces of evidence is the cosmic microwave background, the ancient afterglow of the hot early universe. Over unimaginable spans of time, continued expansion would stretch that radiation to longer and longer wavelengths, making it weaker and harder to detect. Meanwhile, distant galaxies that currently reveal the broader expansion history could pass beyond visibility. In such a future, the universe might offer fewer obvious signs that it began in a hot, dense state at all. This gives modern cosmology a remarkable poignancy. We are not simply discovering ancient truth. We may be discovering it during a window when the evidence is unusually available. A later civilization could be intelligent, careful, and technologically advanced, yet still face a sky that hides its own beginning far more effectively than ours does. The past would remain true, but its traces would be harder to read. In the far future, local galaxies could seem alone. Over enough time, gravity will likely pull the Milky Way and Andromeda together, along with other members of our local group, into one larger bound system. While that local merger story unfolds, acceleration on the wider scale would continue carrying more distant galaxies away. The result is a future in which nearby structures remain together, but the broader cosmic population becomes harder and harder to see. To observers living then, their galaxy system might feel like the whole visible universe. They could study stars and internal motions in great detail, yet miss the grander context that we now take for granted. This possibility is striking because it turns isolation into a consequence of cosmic success. Gravity preserves a local home even as the wider cosmos slips away. The local realm survives, but the evidence for a richer universe fades around it. A civilization could stand inside a magnificent island of stars and still never know how crowded the cosmic ocean once was. Cosmology may be easier now than for future civilizations. That is a remarkable thought, because we usually imagine science becoming steadily easier with time as technology improves. In this case, the universe itself may work against that trend. We live at an epoch when the sky still reveals multiple deep clues at once. Distant galaxies are visible in abundance. The cosmic microwave background can still be measured. Large-scale structure still offers a broad and informative map. These are not permanent gifts. If acceleration keeps carrying remote regions away and stretching ancient light thinner, then the raw evidence available to later observers may be far poorer. Advanced instruments cannot recover signals that no longer reach them. This gives our present era a special status. We are not only technologically capable of cosmology, we are also cosmically fortunate. The universe still shows enough of its history to let us piece together its grand narrative. That combination of timing and intelligence may be rarer than it first appears, and that makes our moment feel unusually precious. We may live in a privileged era for cosmic discovery. Privilege here does not mean comfort or superiority. It means access. Our time may sit in a rare interval when the universe is old enough for complex observers to exist, yet not so old that major evidence has slipped away beyond reach. We can see galaxies across enormous distances. We can detect relic radiation from the early cosmos. We can measure expansion and compare different epochs of history. That combination may not last forever. Earlier in cosmic history, life and observers may have been too rare. Much later, the sky may become too stripped of clues. Between those extremes lies a window in which the universe is both legible and inhabited by minds able to read it. That idea adds a strangely tender note to cosmology. We are not simply latecomers staring into darkness. We may be participants in a rare chapter when the cosmos is willing to explain itself. The timing of our curiosity may be part of what makes understanding possible at all. Dark energy could eventually turn the night sky quieter. Not quieter in sound, of course, but quieter in visible company. The present night sky is already shaped mostly by local stars, yet our scientific instruments reveal a much wider and richer universe filled with external galaxies, clusters, and ancient light. As acceleration carries distant structures farther beyond reach, that broader, visible richness diminishes. The sky becomes less crowded in a deep cosmic sense. Future observers may inherit a universe where the grand background has fallen away, leaving only the nearby and the bound. There is something profoundly eerie about that. The heavens would still be beautiful, perhaps even overwhelmingly so, yet they would be less informative about the larger whole. Silence would enter not as darkness alone, but as missing context. The sky would say less about the universe beyond home. In that future, astronomy might become more inward, more local, and more uncertain about cosmic origin. The night would remain full of stars, yet emptier in what it could reveal. The universe may grow colder, darker, and more isolated. This is the broad emotional horizon of a cosmos ruled for the long term by continued acceleration. As expansion proceeds, galaxies beyond local bound systems recede farther away, fresh star formation declines over enormous timescales, and the accessible universe becomes less populated with visible structure. The great cosmic story does not end in one sudden gesture. It thins. Energy becomes harder to use. New stars become rarer. Distance grows more dominant. Isolation deepens. This picture is often linked with the idea of heat death, though the details depend on how dark energy truly behaves. What matters here is the overall trend. The universe may move toward a future that is not explosive, but austere. The bright and crowded ages give way to longer, dimmer ones. That makes dark energy feel both majestic and melancholy. A hidden driver that now reveals itself through precision measurements may also be shaping the ultimate mood of the cosmos, turning its far future into a place of widening silence and separation. If dark energy strengthens, the future could become far stranger. A constant outward influence already leads to a vast and lonely future, but a growing one would push the story into much wilder territory. The key difference is pace. If the hidden driver becomes stronger as time passes, then expansion would not merely continue. It would intensify. The universe would not just keep opening. It would open more aggressively with age. That possibility matters because even a modest increase could transform long-term predictions. Distances between remote galaxies would grow faster than expected. Horizons would tighten more quickly. Structures that seem safe in a constant expansion picture might face a harsher destiny. This is why cosmologists care so much about whether the effect is truly fixed or only appears fixed so far. The answer does not just fine-tune a detail. It changes the personality of the future universe. A cosmos with strengthening acceleration would be more unstable in its long outlook, and far more dramatic than the already strange future often imagined. One extreme idea ends with a big rip. Few cosmic endings have a name so vivid, and few are so unsettling to imagine. In this scenario, the outward influence connected with expansion grows stronger and stronger until it overwhelms every form of binding in stages. At first, the largest structures lose their hold on one another. Then, smaller scales become vulnerable. What makes the idea so gripping is not only its violence, but its sequence. The universe would not simply blink out. It would unravel level by level. The vast architecture of the cosmos would fail first, and then progressively more intimate structures would follow. That gives the future a terrible kind of chronology. Time would not just carry the universe onward. It would drive a systematic undoing of the bonds that once held reality together. The Big Rip remains speculative, and current evidence does not demand it. But its existence as a serious theoretical possibility shows how deeply the mystery of dark energy reaches into the question of cosmic car, fate. In that scenario, galaxies, stars, and atoms could be torn apart. The progression is what makes this possibility so haunting. First, galaxy clusters would lose cohesion as the growing expansion overwhelmed the gravity that linked them across enormous distances. Later, individual galaxies themselves could be pulled apart. After that, stellar systems might fail, with planets no longer held in orbit. In the most extreme versions, even stars would not survive. Matter that once seemed permanently bound would become vulnerable. The final stage is the most astonishing of all. If the outward effect kept strengthening without limit, even atoms and subatomic structures could be overcome. The familiar solidity of matter would turn out not to be absolute, but contingent on a universe that had not yet reached this final level of disruption. This is one reason the Big Rip captures the imagination so powerfully. It takes the idea of cosmic expansion and pushes it from large-scale astronomy all the way down to the fabric of ordinary existence. Another possibility is that dark energy slowly changes with time. Not every alternative to a constant background leads to disaster. Some models suggest a subtler story, in which the hidden driver evolves gradually across cosmic history. In that case, the universe may still accelerate, but not because of a fixed ingredient with the same strength forever. Instead, the effect could drift, rise, or fall as the cosmos ages. That possibility is fascinating because it turns dark energy from a static backdrop into something more like an unfolding process. The universe would not simply contain a constant mysterious term. It would carry a changing influence whose history matters. A slow evolution could help explain why acceleration became important when it did, and might leave faint signatures in precise astronomical surveys. It would also mean that the future is less locked in than the simplest models suggest. The hidden driver would have a biography, not just a value. Cosmology would then become the task of reconstructing not only what it is, but how it has changed. Some models imagine a cosmic field rolling through space. This picture replaces the idea of a fixed background with something more active and dynamic. In these models, the universe contains a field spread throughout space, and the energy associated with that field changes as it slowly evolves. Physicists sometimes describe this as the field rolling down a potential landscape, which is a mathematical way of saying its energy can shift as the cosmos develops. What makes the idea so evocative is that the driver of acceleration would not be a frozen property of empty space. It would be something still in motion, still changing, still participating in cosmic history. The future of the universe would then depend on where this field is heading and how quickly it moves. A slow roll could mimic a nearly constant effect for billions of years, while still allowing subtle departures from the standard picture. The cosmos would contain not just hidden energy, but a hidden dynamical actor shaping expansion across time. That idea is called quintessence, and it remains unproven. The name comes from an old word for a supposed fifth essence, beyond the familiar earthly elements, and in modern cosmology, it refers to a hypothetical field that could drive acceleration without being strictly tempora. Constant. Quintessence is attractive because it offers motion, change, and a reason the hidden influence might differ across eras. It can make the mystery feel more alive and less like a single unexplained number inserted into the equations. Yet the idea remains speculative. No decisive observation has shown that such a field exists, and many versions of the model must be carefully tuned to match the data already in hand. That uncertainty is part of the intellectual drama. Quintessence is not a fantasy detached from evidence, but neither is it an established component of nature. It stands as one of those beautiful scientific possibilities that may either deepen into truth or fade under better measurements. For now, it remains a candidate, not a conclusion. Quintessence would make dark energy dynamic rather than fixed. That shift changes the whole tone of the subject. A fixed explanation feels like a constant property of the universe, something written into space-time once and for all. A dynamic explanation feels more historical. It suggests the hidden driver has changed, or may still be changing, and that its present strength is only one moment in a larger story. Such a model could help explain why acceleration became important in the relatively late universe rather than dominating all eras equally. It also opens the door to richer futures. The outward influence might weaken, strengthen, or transform further depending on how the field evolves. This gives cosmology an added layer of suspense. Instead of asking only what the hidden term is, scientists would ask where it came from and where it is going. The universe would then resemble a system still unfolding from within. Its acceleration would not just be a fact to measure, but part of an ongoing and dynamic process. A changing dark energy would rewrite standard cosmology. The current standard model works remarkably well, in part because it assumes a simple constant form for the accelerating component. That assumption helps hold together a broad range of observations, from supernovas to large-scale structure. If precise data were to show that the hidden driver changes over time, then the standard picture would need serious revision. Distances, growth rates, geometry, and long-term predictions would all have to be re-examined in light of the new behavior. This is why even small hints of evolution attract such intense attention. They do not merely add decoration to the existing model. They threaten to move the foundation stones. A changing component would also push theorists toward richer explanations, perhaps involving new fields, new symmetries, or new gravitational laws. The effect would ripple across modern physics. Cosmology would not collapse, but it would be forced into a new phase, one where the simplest successful description was no longer enough. Even a small evolution could alter the universe's fate. Cosmic futures are sensitive to long timescales, which means that tiny changes in the present can grow into enormous differences over trillions of years. If the hidden driver strengthens slightly, the universe may head toward a harsher and more rapidly isolating future. If it weakens, acceleration might fade and leave a different long-term expansion story. Even a subtle drift could affect how quickly horizons shrink, how much structure forms, and what distant epochs will look like. This sensitivity is part of what makes dark energy so gripping. The mystery does not need to change dramatically to matter dramatically. A nearly invisible trend in the data today could decide whether the cosmos coasts, tears, or transforms in ways we have not yet imagined. That means precision is not just technical ambition. It is the path to understanding destiny. In a universe governed over immense times by small, persistent effects, even slight evolution becomes a question of enormous consequence. The biggest clue may be whether dark energy has changed before. The universe keeps records of its past behavior in light, structure, and geometry, and astronomers are learning how to read those records with increasing care. If the hidden driver was different in earlier eras, then the evidence should be scattered through the sky in subtle ways. Distances to remote objects may not line up exactly with the simplest model. The growth of structure may show small departures from expectation. Ancient patterns in galaxy surveys may reveal that the accelerating influence we infer today was not always the same. This is why cosmologists look backward so intensely when trying to understand the future. The best clue to what dark energy is may lie in whether it has a history. A constant mystery and an evolving one can look similar for a while, but deep enough observations may separate them. The past becomes the testing ground. To know what will happen next, scientists first need to know whether the cosmos has already changed course before. DESI is building one of the largest maps ever made. This project is vast enough to feel almost mythic. DESI, the dark energy spectroscopic instrument, is surveying the sky on a scale that would have sounded impossible not long ago. Mounted on a telescope in Arizona, it is measuring the light from millions upon millions of galaxies and quasars, turning faint points into a three-dimensional map of cosmic history. The power of that map comes from its reach. It does not simply show where objects are. It shows where they were across deep stretches of time, because distant light arrives from long ago. That means the survey becomes a reconstruction of the universe across ages, not just a snapshot of one moment. There is something thrilling in that ambition. Human beings are not only admiring the cosmos now, they are charting its large-scale past in enough detail to test one of the strangest ideas in physics. It is cartography raised to the level of cosmic interrogation. Its galaxy measurements test dark energy across cosmic time. The real strength of DESI lies in what its measurements let astronomers compare. By recording the spectra of galaxies and quasars, the survey can determine redshifts with enormous precision, which means scientists can place these objects at different depths in cosmic history. Once that layered map exists, the universe stops looking like one flat scene and starts looking like a sequence of eras. Researchers can then test how expansion behaved when the cosmos was younger, and whether the hidden driver of acceleration has stayed steady or changed. That is what gives the project its special tension. Every new redshift is not just another data point. It is another timestamp in the long story of expansion. Enough timestamps, gathered across enough distance, can reveal whether the standard picture truly holds. DESI is asking the universe a demanding question. Has the outward push been the same all along, or has it been quietly evolving while galaxies traced the answer across the sky? Recent DESI results strengthened hints that dark energy may evolve. That is why so many cosmologists have been paying such close attention. In March 2025, the DESI collaboration reported that its first 3 years of data strengthened earlier hints that the hidden driver of cosmic acceleration may not be perfectly constant after Par. Or, the analysis drew on an enormous dataset, including nearly 15 million galaxies and quasars. And the tension became more interesting when DESI results were combined with other observations such as supernovas, weak lensing, and the cosmic microwave background. What makes this so captivating is the scale of the implication. A subtle shift in statistical preference could point toward a changing cosmic ingredient, which would reshape the story of the universe's future and the laws used to describe it. The evidence is not yet a settled revolution, but it has moved from idle speculation into the realm of serious attention. The cosmos may be whispering that its acceleration has a history. Those hints are exciting, but not yet final proof. Science becomes most trustworthy when it resists the urge to celebrate too early. The recent DESI findings are intriguing because they sharpen the case that dark energy might be changing, but the collaboration itself has described them as hints rather than a definitive answer. That distinction matters. A result can be statistically suggestive and still fall short of the level where physicists are ready to call it a discovery. More data must arrive. Different analyses must agree. Independent surveys must either reinforce the signal or expose some hidden weakness in the interpretation. This caution is not a flaw in science. It is one of its great strengths. The universe does not owe us quick certainty, especially on a question this deep. What makes the moment so alive is the balance between wonder and restraint. Astronomers may be standing near a major turning point, yet they are still listening carefully, making sure the cosmos is saying what it seems to be saying. Euclid is mapping billions of galaxies to probe dark energy. Where DESI builds an immense spectroscopic map, Euclid adds another kind of grand survey vision. This European Space Agency mission is designed to chart billions of galaxies across more than a third of the sky and across roughly 10 billion years of cosmic history. That scope alone is astonishing. Euclid is not glancing at the universe. It is undertaking a sustained effort to measure how large-scale structure and expansion have unfolded over most of cosmic time. By capturing galaxy shapes and distances on this scale, the mission can test the hidden causes behind the universe's behavior with extraordinary reach. The ambition feels almost architectural. Instead of focusing on one class of object or one narrow region, Euclid is building a broad map of the dark universe itself. Its goal is to make the invisible legible through pattern, geometry, and depth. In that sense, the mission is not merely observing the cosmos. It is assembling one of the clearest stages yet for dark energy to reveal itself. Euclid studies both cosmic structure and cosmic expansion together. That double approach is one reason the mission is so powerful. Some observations mainly track how distances change with time. Others mainly show how matter gathers into structure. Euclid is built to probe both sides of the story at once. It measures galaxy shapes to study weak gravitational lensing, which reveals how matter is distributed, and it measures redshifts and positions to trace the expansion history and the geometry of the universe. This matters because dark energy leaves fingerprints in both arenas. It influences how space grows, and also how easily structure forms within that growing space. A mission that can watch both effects together gains a much richer view of the mystery. It is like hearing harmony instead of a single note. If one clue points in one direction and the other supports it, confidence grows. If they disagree, the puzzle deepens. Euclid's strength lies in treating the cosmos as one interconnected system rather than a set of separate tests. NASA Roman telescope will also test dark energy precisely. Roman brings another major instrument into the search, and its role is especially exciting because it combines wide field power with dark energy science as a central mission goal. NASA describes the Nancy Grace Roman Space Telescope as an observatory built to tackle essential questions about dark energy. And Roman teams are already preparing surveys of exploding stars and large cosmic structures that can sharpen measurements of expansion history. The telescope has also reached a significant milestone, with NASA announcing in late 2025 that the observatory is now fully assembled. That progress gives the project a wonderful sense of nearness. Roman is not a distant dream on a drawing board. It is a real machine moving toward the sky, designed to gather the kind of precise, wide-field data that modern cosmology needs. When it begins work, it will add a powerful new voice to the effort to determine whether dark energy is fixed, changing, or something stranger still. Modern cosmology now hunts dark energy with multiple giant surveys. That is one of the clearest signs that the field has entered a new era. DESI, Euclid, and Roman are not isolated efforts chasing separate dreams. They are part of a broader movement in which enormous surveys are being designed to test the same deep mystery from different angles. One measures vast numbers of galaxy redshifts from the ground. Another maps galaxy shapes and distances from space across billions of targets. Another prepares to add wide-field infrared power and supernova studies to the mix. This layered strategy matters because dark energy is too elusive for a single line of evidence to carry alone. The mystery touches geometry, structure growth, lensing, and expansion history all at once. To confront something that broad, cosmology has become correspondingly ambitious. The hunt now spans observatories, techniques, and continents. That makes the present moment feel unusually alive. The field is no longer waiting for one lucky clue. It is building an entire global apparatus to force the cosmos to answer. The answer may come from combining many independent measurements. This is often how the deepest scientific puzzles begin to yield. One method offers a clue, another adds pressure, and a third checks whether the first two were fooling us. Dark energy almost certainly demands that kind of combined attack. DESI's recent hints became more compelling when set alongside supernova data, weak lensing results, and measurements of the cosmic microwave background. Euclid is designed to tie structure and expansion together. Roman will add further precision through wide-field surveys and supernova work. The beauty of this approach is that it lets different kinds of evidence test one another. If several independent methods converge on the same picture, confidence grows far more than any one survey could achieve alone. That is why the future of this mystery may depend less on a single dramatic announcement and more on a grand synthesis. The hidden driver of cosmic acceleration may finally reveal its nature when many different observations lock into the same answer at once. Dark energy research has entered a golden age of mapping. There is a special feeling to this moment in cosmology. For years, dark energy was known through a handful of key clues and a model that worked surprisingly well. Now the field is being transformed by surveys vast enough to test that model with far greater severity. DESI is producing one of the largest three-dimensional maps of the universe ever made. Euclid is surveying billions of galaxies across huge stretches of space and time. Roman is advancing toward observations designed to probe the mystery with fresh precision. Put together, these efforts mark a change in scientific style. Dark energy is no longer studied only through selected examples and limited samples. It is being confronted through immense maps, layered evidence, and coordinated programs powerful enough to reveal subtle departures from the standard picture. That is why this era feels golden. Human beings may be living at the moment when cosmic cartography becomes sharp enough to expose the true nature of the force shaping the universe's fate. Dark energy may reveal whether general relativity breaks on vast scales. General relativity has passed some of the most impressive tests in science. It explains the motion of planets, the bending of light, the timing of pulsars, and the existence of black holes and gravitational waves. Yet most of those triumphs happen on scales far smaller than the full observable universe. That leaves one breathtaking possibility still open. Gravity may be exactly right close to home, yet incomplete across the largest distances of all. If that is true, then dark energy may not be a new substance waiting to be found. It may be the sign that gravity itself changes character when space becomes enormous enough. This is why the mystery feels so profound. It presses on one of the grandest achievements in physics and asks whether its success has a hidden boundary. The universe may be using acceleration to expose a limit in our deepest theory, and the clue only becomes visible when we treat the whole cosmos as the testing ground. Gravity might behave differently across the whole universe. That thought is startling because gravity feels like the most familiar force in astronomy. It guides falling apples, lunar orbits, star formation, galactic motion, and the collapse of matter into black holes. We trust it because it works so beautifully in so many places. But the observable universe is vastly larger than the environments where gravity has been tested most precisely. On those immense scales, tiny departures from the familiar rules could build up into major cosmic consequences. A slight change in how space-time responds to matter across billions of light years might look, from our perspective, like a mysterious acceleration. The hidden driver would then be less like an extra ingredient and more like a sign that the rulebook itself bends at the largest scale. That idea gives the cosmos a wonderful sense of unfinished depth. Even the force that built the visible universe may still have surprises waiting, revealed only when human beings learn to read the motion of everything together. The cosmos could be accelerating because gravity changes with distance. This idea invites a dramatic reversal in perspective. Instead of asking what invisible energy is pushing the universe outward, it asks whether gravity itself weakens, shifts, or behaves in a more subtle way as the scale increases. In everyday life, and even inside galaxies, gravity appears familiar. But though the distance is so vast that light needs billions of years to cross them, the law we know may not tell the whole story. If the pull between large regions of the universe behaves differently there, then the expansion history could change without requiring a separate dark energy component at all. This is part of what makes cosmology so exciting. A single observation, the speeding up of expansion, can be read in more than one deep way. It might point to a hidden cosmic ingredient, or it might point back at gravity itself and say that our most trusted description only looks complete until the universe becomes enormous enough to test it properly. Some ideas add new fields woven through all of space. These theories imagine that the universe contains more than the known fields of ordinary physics. Alongside the familiar ingredients, there may be additional fields spread everywhere, subtle enough to escape direct notice but influential enough to alter cosmic expansion or the behavior of gravity. In some models, these fields can interact with matter or space-time in delicate ways that become important only on large scales. That makes them especially interesting because they could help explain why the universe behaves so normally nearby while still producing strange effects across immense distances. The picture is elegant in its own way. Reality would not merely consist of visible matter moving through empty space. It would include unseen layers threaded through the entire cosmos, shaping the background conditions under which galaxies grow and expansion unfolds. Such ideas remain hypothetical, but they show how rich the theoretical landscape has become. The hidden answer may not be one thing. It may be an entire extra layer of cosmic physics. Others suggest space-time itself behaves differently than expected. That possibility reaches even deeper than adding a new field. It suggests that the very arena in which matter, light, and gravity exist may not follow the rules we assumed. In general relativity, space-time is dynamic and responsive, curving in the presence of mass and energy. But some theories propose that its large-scale behavior may depart from Einstein's equations in subtle ways. The geometry itself might respond differently across cosmic distances, or extra terms in the equations might become important only in the broadest possible setting. If so, the accelerating universe would not be revealing a hidden fluid filling space. It would be revealing that the stage of reality has properties we did not fully understand. This is why dark energy feels so philosophically powerful. The mystery does not just ask, what is out there? It asks what kind of things space and time are in the first place. The answer may change not the contents of the universe, but the nature of the cosmic stage itself. Dark energy forces physicists to question what empty space means. For centuries, emptiness sounded like the simplest concept imaginable. It meant the absence of matter, the blankness between objects, the place where nothing interesting should happen. Modern physics has steadily eroded that idea, and dark energy presses the issue harder than almost anything else. If the expansion of the universe is tied to the vacuum itself, then empty space is not passive background. It has physical character, energy, and consequence. It helps shape the motion of galaxies and the destiny of the cosmos. That turns one of the oldest intuitions inside out. Nothingness becomes active. The places between stars and galaxies become central to the story, not secondary to it. This is one reason the subject feels so hauntingly deep. The mystery is not hiding in rare objects or violent events alone. It may be built into the quietest regions of existence. To understand dark energy, physicists may first need to understand why emptiness was never truly empty at all. The vacuum may be the quiet engine of cosmic history. That phrase captures one of the most astonishing possibilities in modern science. The vast reaches between galaxies look still and sparse, yet they may contain a background property that has influenced the universe for billions of years. If the vacuum carries energy, then what seems like absence may be steering the largest motion in existence. It would mean that cosmic history is not shaped only by matter gathering into stars or galaxies colliding in grand displays. It would also be shaped by the baseline nature of space itself, operating everywhere at once with patient persistence. There is something beautiful in that contrast. The grandest changes may come not from explosive drama, but from a constant underlying condition, almost imperceptible locally yet decisive, across the whole cosmos. The engine would be quiet because it would not flash or roar. It would simply remain, acting across time until the universe slowly revealed that even emptiness had been part of the story all along. The greatest mystery in astronomy may be everywhere, all at once. Most mysteries have locations. A black hole sits in a galaxy. A comet crosses a sky. A supernova flares in one distant system. Dark energy feels different because it does not seem confined to a special region or a rare object. Its influence appears in the broad behavior of the universe itself. That means the mystery is not waiting in one corner of the cosmos to be discovered like buried treasure. It may be present in every vast region of space, operating as part of the background order of reality. This gives it an almost paradoxical quality. Something can be universal and still be unknown. Something can shape everything while remaining hidden from direct experience. That is part of why the subject feels so spellbinding. The answer may not lie in going somewhere exotic. It may lie in rethinking what is already everywhere. The universe may be saturated with one of its deepest secrets, and only now are we learning how to notice it. Dark energy turns the universe into a question still unfolding. There was a time when cosmic expansion itself was the great surprise. Then came the deeper shock that the expansion seems to be speeding up. Since then, every answer has opened a wider question. Is the cause a constant energy of space? Is it a changing field? Is gravity incomplete? Is the vacuum misunderstood? The mystery refuses to sit still as a single solved item in a textbook. Instead, it keeps the universe open, unfinished, still in argument with our best ideas. That is one of the most thrilling things about it. We are not living after the great discoveries in a tidy age where the cosmos has already explained itself. We are living during an active chapter of understanding, when the largest known system still withholds one of its central secrets. The universe becomes more than an object of study. It becomes an unfolding question, and modern cosmology is the human effort to keep pace with what reality is still revealing. We know dark energy by its consequences, not by its identity. That may be the most honest summary of the whole mystery. Astronomers can point to accelerating expansion, to the growth of structure, to the geometry of the universe, and to the accumulating evidence that some hidden influence is shaping the cosmic story. Those consequences are serious and measurable. They are the reason dark energy belongs in modern cosmology at all. Yet, when we ask what it actually is, the answer becomes far less secure. The name marks the effect more clearly than the essence. It tells us that something unseen is required, but not whether that something is vacuum energy, a new field, modified gravity, or a clue toward physics not yet imagined. There is humility in that gap, and also wonder. Human beings have learned enough to see the footprint with remarkable clarity, while still not knowing what made it. In that sense, the mystery remains beautifully alive. We understand the shadow better than the source that casts it. As our journey through dark energy comes to a close, we can leave the universe a little wider than we found it. Tonight, we followed one of the strangest discoveries in modern science. We wandered through a cosmos that is not only expanding, but expanding faster with time. We traced that mystery through fading supernovas, ancient patterns in the distribution of galaxies, and the vast maps now being built by astronomers who are trying to understand what may shape the future of everything. We considered empty space as something far less empty than it sounds. We glimpsed possibilities both elegant and unsettling, from a steady cosmic background to changing forces, altered gravity, and futures where the night sky itself may one day grow quieter. And now, having traveled through those immense distances, you do not need to solve any of it. You can simply let the questions drift. Let the galaxies keep their distance. Let the stars go on shining in their faraway silence. Let the great cosmic web rest where it is, suspended across the dark, while your own thoughts begin to loosen and grow soft. If you enjoyed this slow voyage through the universe, I hope you will subscribe, leave a comment, or share this video with someone who might like to wander here too. And if you happen to still be awake in a few moments, there will be another video waiting for you on screen, ready to carry you a little farther into the night. But for now, there is nowhere to go and nothing more to hold on to. Just breathe slowly. Let your body grow heavy. Let the vastness fade into calm, and let the last ideas settle like distant lights, far beyond the edge of thought. Sleep well and good night.